Thank you. So I get to tell you about two projects that we're doing in collaboration with a number of partners, but that live at CIEE. The first of these is the Distribution Monitoring for Renewables Integration project, which follows right on some of the points that Michael made and that were brought up in discussion. I couldn't have asked for a better segue or introduction. Thank you. By way of background, distribution systems used to be really simple and easy. Power systems had power generated in the center and it flowed outward, and downstream from the substations to the end users, it was straightforward. It was not necessary to give too much thought to the moment-to-moment changes in power flow and conditions. If you knew the extreme conditions, what happened at maximum load or what happened during certain kinds of faults, then you pretty much were assured that things would be okay the rest of the time. As we all know, with the advent of more active resources throughout the distribution systems, things get more complicated. When we say smart grid, we generally think about an intelligence infrastructure, big data, communications overlaid onto the legacy electric power infrastructure. And one of the problems that we run into is that somewhere you need to connect physically, right? There's some pieces of this cyber system that involve communications, that involve storing data somewhere, thermostats, people talking to each other. Somewhere you need to connect to the high voltage or medium voltage physical grid to make physical measurements in order to understand what is the state of the system and how do you want to control it. So the problem statement is that really in today's state of affairs, there's fairly little, for very good historical reason, fairly little monitoring that goes on the distribution circuits or feeders as they spread out from the substations. This makes it very difficult for distribution operators to do their job because oftentimes they can't see really what's happening out in the field. What are the conditions? Might you be close to having a voltage violation or some rapid changes? For instance, are the voltage regulators operating too frequently? It's very hard for them to see that. So this project is really about more instrumentation and visibility on distribution circuits, but the question is, how can we pool our knowledge and resources to do this in the most intelligent way? A lot of the utilities that are facing higher penetrations of distributed resources are starting to install more monitoring and to observe effects, to observe specific impacts. But also what we need in the interest of doing good science is to understand the baseline, the comparison, the difference between how does a distribution circuit behave before and after you install a certain amount of distributed generation, and how can we understand in usefully generalized terms the behavior of typical distribution feeders. And Michael spoke about the taxonomy feeders that PNNL produced for the United States. We're interested in producing a set of taxonomy feeders for California. So there's any number of reasons why you need empirical data, empirical measurements to validate feeder models like the GridLab-D that Michael was talking about. Needs to be checked against physical measurement. And there may be things happening on circuits that, in fact, our models are not capturing, but we don't know because we haven't looked to see. So the Energy Commission has funded this research project. We're calling it DMRI. The official title is the Field Study with California Utilities to Assess Capacity for Renewables and Electric Vehicles. And the objective is to coordinate among a set of California utilities, which include the 3 IOUs as well as Sacramento Municipal Utility District, because they have a lot of solar that they're dealing with, to coordinate the collection of empirical data and try to develop a representative sample of circuits and understand their behavior. I'm not going to go through the details of the text slides, but I want to share with you really one of the key points in what we try to understand. In order to instrument intelligently, you need to know, well, what do you need to measure? How carefully do you need to measure it? On what time scale? And also, how densely do you need to put your measurement instrumentation? And traditionally, it was enough to have measurement at the distribution substation. You may have measurement out along a distribution circuit at some particular devices, and really the question is, what kind of coverage do you need to appropriately characterize the behavior of a circuit? This looks familiar. Lloyd has my picture in his slide. This is sort of a graphic way to appreciate the range of timescales that are important in operating electric power systems. We make long-term plans that go out decades into the future, but there are some phenomena that happen on very short timescales. Traditionally, we look at, say, dispatching resources on an hour-to-hour basis, but many of the renewables are changing output on a much more rapid timescale than that. And in my next presentation, I will talk about a measuring technology that is really looking at an even shorter time scale down into the milliseconds and microseconds, sub-AC cycles, so less than a 60th of a second. A lot of interesting things that previously were unobservable are happening at this very small end of the time scale. So the question is, when you install instrumentation, where do you need to look? How carefully is 15-minute data, as you get from customer meters, tell you certain things about energy consumption. They don't tell you about real-time state of the circuit. How carefully do you have to look? Minute by minute, second by second. So that's one of the things we want to ascertain together. And also, again, in the distance scale, how close together do you need instrumentation to be able to accurately characterize what's happening? And a lot of interesting power quality phenomena happen at the very small distance scale. So this DMRI project really begins with pooling existing data. And as was also mentioned, it's not easy for a utility company to just share data because there are really important security and privacy concerns. So one of the things that we have to do is be very careful to anonymize data that comes from particular circuits to make sure that it's not revealing inappropriate things. So for this project, we're collaborating with the UC San Diego Supercomputing Center that is actually receiving data from utilities and then scrubbing it of identifying information so that we can create a collective database in which I can look at a circuit and have it characterized by important physical variables such as, what's the weather zone and what types of loads are there, roughly speaking, but I won't know which company does it come from. So that's one advantage of having this collaborative approach. The other advantage certainly is to get a broader, more representative sampling. And we're looking at, for the first phase, 20 circuits from each utility to give us the initial set to look at what do we have there. And really the circuits are those that include measurements beyond the substation. But we will likely find that in order to fully characterize and understand what is happening on these circuits, we really want more instrumentation. And so the phase 2 is really, of this project, is about collaboratively figuring out what is the smart way to add to the existing monitoring capability that's there so that we can fill in the gaps in our knowledge and understanding. Ultimately, we would like to think that this will lead to permanent monitoring, that we will become habituated to a better and more careful understanding of what's happening on these circuits. We may also find out about things that we didn't know were happening. We certainly want to provide a baseline for comparison. And also, I should say that UC Irvine is one of our research partners, and they we'll be working on model validation, in particular for models that try and capture the behavior of inverters and different types of distributed resources. I'm going to segue to my other presentation and do questions jointly at the end, I think. So I'm going to click on that link, and it's beautiful. I love it. So this other research project, which was funded by the Department of Energy, really is spiritually related to this, to the DMRI, because it follows in the same philosophy of better understanding distribution system behavior. But here we're playing with a new toy. Here we have a new instrument that is going all the way to the cutting edge of what it's physically possible and mathematically realistic to observe and measure. So this is a project about synchrophasors. Indulge me. Let me say just a few words about what are synchrophasors for those of you who are not familiar. Alternating current changes direction here in the United States 60 times a second. For the connected parts, we call them the synchronous parts, which are the western United States, the eastern interconnect, and Texas. The interconnect is called synchronous because the ups and downs of voltage and current are simultaneously. To a first approximation. In reality, the laws of physics counterintuitively demand that it can't be exactly synchronous, but there has to be a little bit of a shift in time between the voltage waveform at one location and the voltage waveform at another. And it's that little difference, the delta, that we're interested in measuring. We can understand that in terms of the power flow between two different locations. So if you have one rotating generator in one place and one in another, their positions will actually be slightly off by an angle that corresponds to how much power is flowing between those locations. And this is the equation that approximately describes that. So this phase angle delta, that slight difference in timing between the voltage waveform, is really the key to understanding all the behavior of the AC grid, the power flow in the steady state and also the power flow as dynamic and interesting things happen, instabilities, oscillations, and so forth. This is your diagnostic key. In the past, it was never possible to empirically measure that little delta because to do it, you need a time reference. It doesn't mean anything to measure the voltage phase angle at one location at 3 o'clock if you don't know exactly what time it is at another place where you're also measuring that voltage, right? So you need to have these very precisely time-stamped measurements down to on the order of microseconds to compare them. And this really became possible in the late 1980s when the first synchrophasors were developed and implemented. And so here's a one-line diagram of the Western grid, and then you now have synchrophasors. Let me actually skip ahead, coming out like mushrooms out of the ground after the rain because they turn out to have such great diagnostic power. This was in 2010. This was in 2012. And so you could see that these transmission synchrophasors are being rapidly adopted and, in fact, have given rise to a number of really interesting diagnostic applications, such as being able to observe oscillations that we never before knew or had reason to suspect that they existed, except for the occasional outage that happened for no good reason, right? Let me go back to this version of the timescale, which is to say that we're looking here at intervals down to less than a degree of angle. Now, the degree refers to the oscillation of voltage back and forth. So one complete cycle would be 360 degrees. 1 degree would be 1/360th of 1/60th of a second. That's about the resolution of your typical transmission phasor measurement units, or PMUs. At the distribution system, which is where we are going to look, you need a much better resolution because you're looking at shorter distances and smaller power flows, so the angles are going to be smaller. You need a more sensitive instrument. And this is what our colleagues at Power Standards Lab have now built, a device that is going to, we're actually shooting for 100th of a degree of resolution. So we're talking about milli-degrees rather than full degrees. This is in the context, excuse me, of other kinds of interesting power quality measurements that we hope will help us interpret the synchrophasor data. So the concept for the Micro-PMU, the highly accurate phasor measurement unit, is to deploy it around distribution systems, have the different units talk to each other, and we're working with our engineering school here using the SMAP approach for really a fast and efficient, appropriate data management approach to grab the data from the individual synchrophasors and bring them together at a node to compare the values and to begin to understand what does this voltage angle information tell us, what actionable intelligence does it give us about the distribution feeder. No one has done this on distribution systems, first of all, for the reason I mentioned, which is that the measurements are more challenging. You have to look much more carefully than at the transmission system if you want to get useful information out of voltage angle. There is a difficulty in making the business case for installing a measuring device at the distribution level when you only have so many customers that are really affected by the part of the circuit that you're measuring there. Much easier to make the case to spend a couple tens of thousands of dollars for a transmission level PMU. Much more difficult to make that at the distribution level. So you need a less expensive instrument, but one that's more accurate. Now, the main thing, though, is that historically there was no need for measuring voltage angle at the distribution level. There wasn't even really a need to measure voltage magnitude in real time because, as I said, things used to be simple and straightforward. This is now, as we all know, changing. Here are some pictures of the device that Power Standards Lab has built. They have sold internationally for years this device called the P-Cube, the power quality monitor, and the Micro-PMU piggybacks on that platform. It combines the voltage angle measurement, like I said, with a whole power quality recorder. You can look at it in real time. You can look at it archivally. The big difference is having this GPS antenna. And the big challenge is accounting for all the different time delays, the different latencies that get into the picture when you're trying to compare measurements on the order of microseconds. Here's a picture of the newest version. So it's a very high sampling rate. That's so that we can pick up harmonics. And the philosophy here, just like with the DMRI project, is that in order to know what resolution we need to start by oversampling so that we can then back off. We can't make crude measurements, and we'll never know if we might have seen something had we looked more carefully. Power Standards Lab has built the first prototypes. They're in Alameda, and the first test actually is about just comparing two Micro-PMUs, and they have their two GPS receivers here, or they're put in different corners of the roof, different locations, and comparing to see if they're actually consistent in each other's measurements. So far, so good. We are about to bring some of them to Soda Hall, to the lab here, and then our intent is to start measuring things that happen on the electric circuits here on campus. One of the beautiful things about this instrument is that it can look at the distribution circuit from the secondary side. In other words, if you wanted to just go really cheap and quick and easy, you could plug it into a single-phase 120-volt outlet in the wall and measure the phase angle. You then have to account, if you want to draw conclusions about what's happening on the primary distribution circuit, you need to account for the things that are in between, such as a distribution transformer, and we're working on techniques for doing that. It certainly would save a lot of money to be able to have good visibility of medium voltage distribution circuits by connecting on the secondary side. It also actually raises some interesting questions about, well, anyone who can buy one of these things, which is roughly the cost of a nice mountain bike, and who has the analytic capabilities to interpret the data, could, in principle, see what's happening on the circuit. Another complication, actually, to mention is that, of course, we have 3 phases on the distribution system, and we need to learn about all 3. So not all of the PMUs would be plugged in to a single phase. There's more details I could say about the installation, but just quickly, sort of the plan is to try out the device to build the communication infrastructure, and we're going to start, well, there's a couple things. We can start by having them talk to each other on Ethernet. They have camera SD cards as a backup for archival data. We also want to try 4G wireless as a communication layer, because it's promising that it would meet the needs in terms of the latency as well as the bandwidth that you need and the data volume. We don't know yet how much of the data actually need to be communicated. It depends on the application. It depends on what you want to do with it. There's a lot of flexibility here. The device can send out data in fire hose mode. That might not be what you want. You might want to have a more realistic sampling interval. You might want it to send you information by report by exception if interesting things happen. These are still things we have to play with and figure out the most appropriate installation for the applications you want to use. Our next step is going to be instrumenting some small number of distribution circuits, working with partner utilities, and we're in conversation with several utilities about hosting these, and really understand fundamentally what can we learn from directly measuring the voltage angle that we couldn't learn before. Just to give you some ideas of the applications, with explicit measurement of voltage phase angle, it becomes trivial to see which way the power is flowing. And reverse power flow can certainly be a problem for utilities if their protective systems are not anticipating that, or even if the voltage regulators aren't expecting an inverted profile. Another application, and this is where the angle measurement and the high resolution, the high sampling rate could be useful, is to see if there are interaction phenomena between and among certain distributed energy resources. So just as an example, if you have 2 inverters, there may be oscillations that happen, which it could be that these aren't creating any problems, but we'd like to look and see what's out there. Actually, I like Merwin Brown's name for this application, which is shark detection. It was like the oscillations in the transmission system that nobody knew we were swimming with sharks, and we'd just like to see what's down there. We may or may not want to take any action about it, but you'd like to see. Another application potentially is to detect not only the occurrence, but the risk of occurrence of the thing we affectionately call FIDVR, which is essentially voltage misbehavior as a result of single-phase air conditioners stalling out. When the voltage goes low, then they actually draw more current and they make the voltage go lower. Your capacitors try to correct for this. A whole number of unpleasant things happen, and it would be really nice if you could catch this phenomenon before it happened. So that's a research question for us. Can we see this? These are actually the applications that in conversation with some of our utility partners seem to be of interest to them. I could mention a lot more. In fact, on this slide is sort of a longer list of things you could do. And our task right now, actually this quarter, is to down select which of these applications we are going to study more carefully and develop algorithms for and try out in the field. it's a fine print because we can come back to this slide in questions if you like, but it's really a whole range of steady state and transient dynamic analysis. A number of the utilities we've talked to are very interested in helping understand faults, just locating a fault rather than having to go on location, but being able to pin it down to within so many feet or yards from looking at the angle measurements could be a very useful kind of application. In the long run, my interest in this really is in enabling a much higher level of contribution from distributed energy resources to the grid. Right now, for many utilities, the priority is to avoid bad things that might happen. It is understanding and mitigating unintended impacts, such as the hyperactive voltage regulators or other things that just, whether it's power quality issues or things that make the management of the system more difficult, we'd like to better understand it. In the long run, really, we'd like to be able to recruit distributed resources more effectively to work together to provide services to the grid. I should say that visibility and situational awareness is important not just for distribution operators, but the more interesting things happen at the distribution level, the more it actually becomes of interest to the transmission operators and the California ISO, for instance, to have some understanding of what's going on behind that substation, which traditionally they can't see, that allows them to maybe infer and predict a little bit better what are the vulnerabilities, what might it be doing in the next minute. Certainly, near-term advantages we're hoping for are improved reliability just due to better diagnostics, faster service restoration. Any number of these applications deal with faster correct identification of the circuit topology and then addressing it and changing it. So in my mind, this really, in the long run, may change how we understand distribution systems as something to be actively managed. To manage it, we have to observe it first. I don't think I mentioned in my first slide all the project partners. Lawrence Berkeley National Lab is an important project partner with us in this because, as you can imagine, a big part of the understanding the usefulness of the measuring tool is modeling the circuit and representing it, and they have some great capabilities there. So CIEE, Lawrence Berkeley Lab, UC Berkeley, and Power Standards Lab are working together on this. I think this is my last slide, and I'm happy to take questions. Okay, I'm done. No.
These devices that are GPS time propagation based been analyzed for vulnerability? Have these commercial devices been analyzed for vulnerability to GPS jamming or worse yet, spoofing?
That's a good question, and I wish Alex McEachern were here to address that. I think the answer is yes, we are vulnerable to mistakes in the GPS signal, although the Micro-PMU does have its internal clock also. So if something goes very wrong, it will know that it's wrong. And there is a difference between having bad data and not knowing it, and having bad data and knowing that it's bad. I don't think that we're quite at the point yet where we can talk about, so what mitigative steps are we taking? But certainly the bottom line of the accuracy and the quality of the data that you're going to get is in the quality of the time stamping. That's certainly true.
So if I could comment on that, because I spoke with Alex about this at our last meeting, there's a surprising variance in GPS receivers as to which ones can be successfully spoofed into thinking they have an appropriate signal by having their automatic gain value slowly changed over time as you impose a new signal on them. And it looks, at least initially, like this is not necessarily a problem that we'll see in these particular units, or they're not as sensitive to this problem as some other units that are out there, but certainly it'll be looked at very carefully because it is a security concern, yeah.
And I would add to that, I would add to that really the security concern is a different one when you're looking at diagnostic applications than when you're looking at applications in which you're actually going to take control actions based on the information. And naturally, we're starting with diagnostic uses where the stakes are not quite as high as if you're actually going to flip a switch. So there will be some years of experience between starting to use the microsynchrophaser data and actually taking your chances by operating something based on it.
Okay, thank you very much.
Thank you.